years wide. It is at least twice as big. We've been living in a double-sized galaxy. We taught in every classroom, graphed in every textbook, and calculated in every paper. New technology has just exposed the truth, and it will change everything. How we assess the universe when Andromeda strikes us, whether we are alone. If you want to discover how scientists rewrote the size of our homes, click the like button and subscribe. This is the story of the most significant correction in contemporary astronomy. Prepare yourselves. We begin. Open your astronomy textbook. Find a diagram of the Milky Way, that exquisite spiral with crisp measurements showing 100,000 light-years across it, is entirely incorrect. Not just slightly off, not obsolete by a few percentage points, but by a factor of 2. Every poster in every school, every documentary, cartoon, and every reliable Wikipedia diagram depicts a galaxy. Scientists have known for years that something was wrong because the size was just half of what it should be. However, the data arrived in fragments, hints, and anomalies that did not match the models. Stars moving too quickly on the edges, satellite galaxies circling too far away, and mass calculations that never balance. The measurements then began streaming in from the Gaia spacecraft, James Webb observations, radio telescope surveys, and charting hydrogen clouds on the edges. Each new device exhibited the same shocking pattern. The Milky Way goes far beyond where we thought it ended. The issue isn't that astronomers were sloppy. The issue is that we have been trying to measure our galaxy from within it. Imagine standing in the heart of New York City and attempting to define its borders. You can't see the edges. You cannot get a sense of perspective by going outside. You're surrounded by buildings, lights, and noise. That's us floating in one spiral arm, 26,000 light-years from the center, surrounded by stars and dust. For decades, scientists followed a basic procedure. They glanced at the brightest stars they could see in every direction as the stars thinned away. They drew a line, which became the edge. 100,000 light-years. Case closed, but it was never so simple. The galaxy does not have a distinct edge, like a dinner plate. It disappears gradually. Stars spread forth in thin streams and clouds. Dark matter, which is unseen and huge, extends even farther. The previous measurements simply followed the brightest portions, the obvious portions. They missed the massive halo of stuff that surrounded everything. This is what altered everything. Scientists began tracking stellar streams. These are streams of stars ripped from smaller galaxies that the Milky Way swallowed millions of years ago. The streams orbit across space like cosmic fossils, revealing the true gravitational pull of our galaxy. Researchers mapped these streams. They discovered them circling far beyond the predicted boundary, perhaps 200 light-years or more. The Milky Way is a massive structure, and we've been measuring its shadow. This discovery does more than merely tweak the numbers in a textbook. It fundamentally alters our understanding of galaxy organization. It varies when Andromeda will crash with us. It doubles the amount of area we require to seek for life. Every calculation based on the former size has now crumbled, but the most concerning aspect is that if we got our own galaxy this incorrect, what else have we miscalculated? How many more galaxies are twice the size we think? Imagine you're blindfolded and standing someplace in the Sahara Desert. Your job is to measure the entire desert. You cannot remove the blindfold. You cannot utilize GPS. You can only feel the sand under your feet and hear the breeze. How precisely could you map it? That is what astronomers face when surveying the Milky Way. We are sitting on a rock orbiting an ordinary star in an outer spiral arm. Dust clouds obscure our view in nearly every way. The galactic center is concealed below massive layers of gas and debris. We can view around 10% of the galaxy with optical telescopes. The rest remains hidden in infrared. Using radio waves and darkness as comparisons, Andromeda is easily measured. It is around 2.5 million light-years away. We see everything at once, edge to edge and top to bottom. We can picture and map its spiral, arm count, and star clusters. Measuring our own galaxy is like trying to photograph your face without a mirror while standing in a fog bank. Early astronomers had no choice. They measured what they saw. They monitored Cepheid variable stars, which pulse at predictable intervals. They determined the distances to GLO clusters, which are ancient balls of stars orbiting the galaxy core. They pieced together a map, as if they were building a puzzle while blindfolded. The breakthrough occurred when scientists realized they could employ motion instead of light. Everything in the galaxy revolves around the center. Stars, gas clouds, complete star clusters. They move at different speeds depending on the mass pulling them. Measure the speed, calculate the mass, and estimate the size. But this is where things get interesting. The speeds didn't match. Stars at the galaxy's edge moved far too quickly. According to the observable mass, they should fly out into space. Something invisible was keeping them in orbit. Dark matter forms a huge halo that wraps around the galaxy like a gravitational cocoon. This is where previous measures failed. They simply counted what they saw. Visible stars, blazing gas, and a dazzling nebula. They overlooked the invisible mass, the dark structure that kept everything together. That was a mistake. Modern telescopes altered the game. The Gaia satellite monitors the precise movement of more than 1 billion stars. Radio telescopes map hydrogen gas as it extends toward the outer halo. Infrared equipment can see through dust clouds, which obscure visible light. Each technology uncovers a new layer of the galaxy. Researchers began using satellite galaxies as test masses. There are dozens of dwarf galaxies that orbit the Milky Way. The giant Magellan Cloud and the little Magellan Cloud Sagittarius dwarf. These galaxies orbit based on our entire mass, both visible and unseen. Track their motions and map the true gravitational field. When scientists compiled all of this information, the results surprised them. The Milky Way isn't the medium-sized spiral we expected. It's a heavyweight, a galactic giant, double the width and thrice the mass. And if measuring from the inside is as difficult, what happens when we try to measure farther away? Stellar streams seem exotic, but they are actually galactic murder scenes. Evidence of violence is frozen in time. Millions of years ago, tiny galaxies came uncomfortably close to the Milky Way. Our gravity seized them, separated them, and stretched them like taffy. Their stars did not disappear. They dispersed into long rivers of light that surrounded our galaxy in thin streams. Some of these streams are larger than Earth's whole orbit around Sunday. Others include thousands of stars moving in perfect formation. We'd never paid attention to them before. They appeared to be background noise, dim, distant, and inconsequential. But they are the most accurate rulers available for measuring the galaxy. Here's why they matter. Gravitational forces dictate the orbital trajectories of stellar streams. Every star in the stream moves according to the overall mass tugging on it. Measure the stream's path to determine the gravitational field. No guessing or assumptions. The Sagittarius stream is the most well-known example of pure physics. It loops around the Milky Way several times, like a ribbon on a present. Scientists traced the stream across the sky and discovered that it extended well beyond the previous galactic boundaries. The stream continues to flow, as does gravity in the Milky Way. Then came the GD1 stream, a tiny river of stars in the outer halo. Researchers investigated its curve and discovered something impossible. The stream curved in ways that needed significantly more mass than the visible galaxy had. Either physics was broken, or we were missing something huge. Dark matter is always dark matter. The streams displayed it like invisible ink under ultraviolet light. The gravitational pull that shaped these star rivers came from material. We can't see material that extends twice as far as the visible stars, but what follows is much stranger. Scientists discovered streams orbiting at distances we assumed were cosmic space, empty gaps between galaxies, but they were not. These streams demonstrated that the Milky Way's effect extends further than anyone believed. Our galaxy does not end at the visible boundary. It keeps pulling, claiming territory, and asserting control. The Orphan Stream is really haunting. It orbits so far away that scientists disputed for years whether it belonged to the Milky Way or another galaxy. New measurements verified this. The stream is ours, implying that the Milky Way reaches at least that far. Every fresh stream discovery, kilometers have been added to the galactic radius. 5,000 light-years here and 10,000 there. The figures increased by 120,000 light-years. Astronomers sorely needed something, and 180,000 stellar streams provided it. The ground truth. You can discuss where the visible disk's edge is. You might debate where darkness meets cosmic space, but you can't disagree with a stream of stars orbiting data. Their route is the truth, and the truth is constantly pushing the boundaries outward. 200,000 light-years is well beyond what is comfortable or explainable with old models. The stream said so. The arithmetic stated, the observation said, and the question of how big the Milky Way was no longer relevant. The issue arose, how did we miss it for so long? You are looking at the Milky Way right now, or you believe you are. What you see is the skeleton, the bones, and the brilliant areas. 90% of the galaxy is invisible. Dark matter is no longer a theory. It is confirmed, measured, and mapped. We can't see it directly, but we can see the impacts everywhere. Stars move too quickly. The galaxy spins without breaking apart. Light from distant objects bends around the visible bulk. The evidence is strong in the Milky Way. Dark matter does not just add weight, it constructs the structure. Consider a building where you can only see the windows, not the steel frame that holds them up. That's our galaxy. The stars are windows. Dark matter serves as the framework. Scientists think that dark matter surpasses visible stuff by a factor of 10 to 1. Every visible star contains 10 times more unseen mass nearby. This debris forms a large halo surrounding the galaxy, spherical and diffuse, extending well beyond the visible disk. The previous measurements omitted this halo. They concentrated on the colorful spiral arms, the incandescent core, and the prominent features. The galaxy seemed to be 100,000 light-years across, because visible stars drop out at that point. But dark matter continues to exist. It is at least twice as long as before. Consider it like an iceberg. Above the water, you can see the visible galaxy beneath the surface. A 10 times larger ice mountain lies hidden from sight. That's the dark matter halo. The true size includes both researchers. When light from a distant galaxy passes near the Milky Way, gravitational lensing is used to map its halo. Our dark matter bends it somewhat, measure the bending, and compute the mass. The results were alarming. When you include the dim outer areas, our dark matter halo spans about 400,000 light-years. But here's the twist. Scientists argue where to draw the boundary. When does the Milky Way come to an end in intergalactic space? Begin? Is this where the density of dark matter declines to a half-quarter or a tenth? There is no formal edge, only a steady fade to nothing. Astronomers utilize the OWL radius as a practical measurement. This indicates the point at which material becomes gravitationally bonded to the galaxy. Within this radius, everything orbits together. Outside space is absolutely empty for the Milky Way. The burial radius is roughly 200,000 to 250,000 light-years. Double the previous estimate, all due to unseen bulk. This fundamentally alters our understanding of galaxy structure. Galaxies are not starry islands floating in empty space. They are massive halos of dark matter with stars scattered across the core. The visible portion is decorative. The invisible component is substance. And if our galaxy contains this much hidden mass, then so does every other galaxy. The universe has just become a lot heavier. The Milky Way isn't alone. Dozens of smaller galaxies orbit us, similar to moons orbiting planets. We call them satellite galaxies, and they have rewritten our cosmic address. The Malin Cloud is the largest seen from the southern hemisphere as a cloudy smudge. It has 30 billion stars. The little Malin Cloud sits close, alongside 7 billion others. Then come the dwarf galaxies, Sagittarius Dwarf, Draco Dwarf, or Ursa Minor Dwarf. Each is a small galaxy, complete with its own stars, its own history. It has its own orbit. For years, astronomers thought of these satellites as independent objects passing past, until fresh observations revealed the truth. They're not passing by. They are trapped, circling within the Milky Way's gravitational field of influence. This revelation transformed everything. When you measure how fast a satellite orbits, you may determine the mass that keeps it in place. More mass equals tighter orbits. Less mass means that items drift away. The satellite galaxies orbit at precise distances and speeds, revealing our overall gravitational pull. A big Malin cloud, located 160,000 light-years away. It orbits the Milky Way once every 1.5 billion years. To maintain that orbit at that distance, our galaxy must be huge. Far more large than previous estimates. Researchers tracked dozens of satellites and discovered the same pattern. They all orbit farther away than expected. They all go faster than expected. The only explanation: the Milky Way is larger and heavier than scientists expected, but the true breakthrough came from tidal streams. When a satellite galaxy approaches too closely, the Milky Way rips it apart. Stars are pushed away in vast trails. The Sagittarius dwarf is now being destroyed in this manner. The stars spread over the sky in a torrent. These tidal tails, which span the entire galaxy, serve as test masses. They show where the gravitational field is greatest, weakest, and where the boundary lies. Map enough streams, and you can map the galaxy's edge. What scientists discovered stunned them. The streams went well beyond the putative galactic limit. Some reached out beyond 150,000 light-years. Others reached 200,000 Dao. A few indicators pointed to material much further out. The satellites screamed the truth. The Milky Way is massive. This has immediate ramifications. If our galaxy is this large, the local group of galaxies must be redrawn. The distance between us and Andromeda is lower than we expected. Each galaxy's gravitational effect extends farther. Collisions occur sooner. Merges begin early. Each satellite galaxy became a data point. Every orbit is a measurement tool. They painted an image of a galactic giant, not the medium spiral we had envisaged. And now for the haunting part. Some satellites orbit so far away that we still discover them every few years. Astronomers discover another dwarf galaxy buried in the data. Every new discovery pushes our boundaries a little further. How many more are there? How much bigger does the Milky Way really get? 200,000 light-years. The number is so large that it stops, which might imply anything. Your brain cannot process it, visualize it, or hold it. Let me make things worse. Light travels at 186,000 miles per second in 1 year, covering around 6 trillion miles. Multiply this by 200,000 Dano. The Milky Way is around 1.2 billion trillion miles vast and still meaningless. Let me try another method. If you could move at the speed of light, the universe's maximum speed, it would take you 200,000 years to cross the galaxy. When the light from one edge eventually reaches the other, mankind have progressed from primitive hunter-gatherers to a spacefaring society that has collapsed and evolved multiple times. Put another perspective. Imagine the Earth was the size of a grain of sand. The Milky Way would spread farther than the distance between Earth and Saturn. Actually, the light you see from the distant edge of the galaxy predates contemporary people, Neanderthals, and Homo erectus. That light has been traveling since our ancestors. We're still living in trees. The scale defies human intuition. We evolved to understand distance. We can walk for miles, maybe even hundreds of miles. Our brains never develop circuitry to grasp billions and trillions of things. But here's where it becomes personal. The incomprehensible size matters to you. Right now, double the galaxy size equals double. The volume of space rises with the cube of the radius. If the galaxy is twice as broad, it has 8 times the total volume, 8 times more space, 8 times more stars, and 8 times the number of planets. The previous estimate suggested 200 billion stars. The current estimate is closer to 400 billion, or more. Every single one of those stars may have planets. Every planet could have moons, and each moon could have underground oceans. The number of possible lifelong homes has just doubled. Consider what that means. If life is rare, 1 in a billion star systems, we have simply increased the possibilities by 200 billion. If intelligent life exists someplace out there, we have increased the chances of finding it. Or they discover us, but the size also affects our survival timeline. The Andromeda Galaxy is approaching us at 70 miles per second. Galaxies do not collide in the same way as cars do. They merged. Stars move between each other. Very few actually strike, but the gravitational chaos alters everything scientists had previously anticipated. The Andromeda collision would occur in 4.5 billion years. A larger Milky Way indicates a greater gravitational reach. The galaxies will begin to interact sooner, perhaps in 4 billion years, or even less. If humanity survives long enough, your children will see the night sky alter. Andromeda will grow larger and brighter, eventually covering half of the visible sky. Then the galaxies will dance around one another. Spirals intertwine, before eventually coalescing into one giant elliptical galaxy. 200,000 light-years is more than simply a figure. It is your future, your past, the stage where every human narrative ever told takes place in one tiny spot. And we just realized the stage is twice the size we anticipated Andromeda would be. This is not a speculation, it is an established reality. Our neighboring galaxy is speeding at us. At 70 miles per second, the collision is unavoidable. For decades, experts projected that the impact would occur in about 4.5 billion years. Mark your calendars, except that those figures are based on the previous galaxy sizes, which are smaller, milkier, and gravitationally farther apart. Andromeda, a larger Milky Way, alters the timeline. Gravity reaches further. The galaxies will begin to draw on each other sooner than planned. Their huge dark matter halos will interact first, extending hundreds of millions of light years beyond. When the halos make contact, the collision begins. Imagine two people heading toward each other. If they are both larger than you expected, they will collide sooner. The same logic applies at a galactic scale. New models imply that the contact might begin in less than 4 billion years, possibly 3.5 billion. The exact timeline is dependent on accurate measurements. We're still gathering, but the trend is evident. Larger galaxies indicate that they formed earlier. Contact is what occurs when galaxies collide. First, the outer halos start to merge. Dark matter can penetrate. This phase is unseen, yet gravitationally powerful stars destabilize due to the pull of both galactic centers and orbits. Some stars are thrown into intergalactic space. Others rush toward the cause. Then the visible disks collide. Not a crash, but more like two clouds going across each other. Stars are so far apart that direct collisions are extremely uncommon. You could fit millions of Earths between adjacent stars, but gravitational chaos exists. The star formation explodes. Gas clouds compress, causing new stars to ignite throughout both galaxies. The Milky Way and Andromeda will orbit each other several times, swirling and twirling as each pass strips away. More material tidal pressures tear spiral arms, scattering star streams in all directions. The formerly exquisite structures are bent, mangled, and unrecognizable. Eventually, perhaps 1 billion years after first contact, the galaxies will merge altogether. The end outcome is a large elliptical galaxy. There are no more spiral arms or ordered disks, only a blob of 4 trillion stars rotating in random directions. Astronomers have already dubbed this future galaxy Milkometa, a charming term for the death of two old spirals. But here's the big question. Will Earth survive? Will the Sun survive? Will humanity be around to witness it? First, good news. The Sun is expected to survive the merger. It is far enough from the galactic center to likely avoid the most violent regions. Earth might be thrown into a new orbit or hurled altogether into cosmic space. Alternatively, keep roughly where it is. The odds favor survival. Unfortunately, the Sun will have died by then. Our star has approximately 5 billion years of fuel left. The Andromeda collision occurs just before the Sun dies. We might gain a front-row ticket to the early stages if a larger Milky Way moves up the time frame. The show begins sooner, and this is the part no one talks about. What if Andromeda is also larger than our measurements indicate? Their estimates could also be inaccurate. If both galaxies are larger, the collision occurs even faster. The gravitational chaos grows more extreme. The final united galaxy is even more enormous. We're already witnessing early symptoms as Rotor's halo expands toward us. Our halo extends toward them. The halos might already be touching. The collision might have already started, slowly becoming invisible in the black matter, enveloping both galaxies. 4 billion years may seem like an eternity, yet on cosmic timeframes, it is only tomorrow and tomorrow. Just got a little closer to mass. Everything comes down to mass. The Milky Way just gained weight. The analysis revealed a significant amount of weight, trillions upon trillions of solar masses. According to previous estimates, our galaxy had around 1.5 trillion times the mass of the Sun. Most of it was dark matter. The new results indicate 4 trillion solar masses, or more. We tripled the mass estimate in less than a decade. Here's what a solar mass is. The Sun weighs around 2 billion kilos, a huge number that becomes abstract. 1 solar mass. For example, the Earth weighs 300,000 times less than a Sunday. Jupiter weighs 1,000 times less. Except for the Sun, everything in our solar system accounts for less than 1% of the total solar mass. Now multiply the Sun's mass by 4 trillion. That's the Milky Way, a gravitational giant. Where did all the extra bulk originate from? Has the galaxy suddenly gained weight? Did substance emerge from nothing? Obviously not. It was always there. We simply could not measure it correctly. Most of the extra mass is dark matter, which is invisible and undetectable except through gravity. The previous observations focused on visible stars and gas, estimating dark matter indirectly. Using galactic rotation curves, stars orbit. The center moves at speeds controlled by mass. Measure the speeds and determine the mass. However, such observations only sampled the inner galaxy, the region where stars are abundant and observations are simple. Nobody has correctly measured the outer halo, where dark matter dominates. That was a mistake. New techniques altered everything. Satellite galaxy orbits enabled direct mass measurements over vast distances. Stellar streams traced the gravitational field in the outer regions. Computer simulations compared our galaxy to thousands of simulated galaxies of known mass. All techniques agreed, 4 trillion solar masses. The Milky Way is a heavyweight. This has huge repercussions. More mass equals greater gravity. Stronger gravity allows us to keep more satellite galaxies in orbit. We can remove stars from passing neighbors more easily. We now have a more comprehensive control over the local group. Andromeda has always been considered the larger sibling, the Alpha Galaxy, but new measurements reveal we may be equals or even larger. The Milky Way and Andromeda have approximately the same 4 trillion solar masses. Each of the 2 galactic superpowers on a collision track has more mass, which affects how we formed galaxies expand by eating smaller ones. The bigger you are, the more you have consumed a 4 trillion solar mass. Galaxy has a bloody history. We devoured hundreds of dwarf galaxies, maybe thousands. Every satellite stream in the halo is evidence of a meal, a galaxy that got too close and paid the price. The Sagittarius dwarf is being eaten right now, torn apart, digested its stars scattered across the Milky Way disk in a few 100 million years. No trace of it will remain, except ghosts, in the data. This is how galaxies grow: cannibalism, galactic empire building. But here is the terrifying part. If we are 4 trillion solar masses, and most of that is dark matter, we live in a galaxy made mostly of invisible material. 90% of everything around us is something we cannot see, cannot touch, cannot directly detect. You think you know where you live. You think you understand your cosmic neighborhood. You are wrong. You are swimming in an ocean of dark matter, and you cannot feel the water. 4 trillion solar masses of mostly invisible material that is home. That is the Milky Way, and we just realized how enormous it really is. The galaxy does not end where the stars stop. It keeps going and going far beyond anything visible into the realm of pure dark matter. Scientists call it the dark matter halo, a massive spherical cloud of invisible particles surrounding the entire visible galaxy. This halo is not a minor feature. It is the dominant structure, the foundation, the cage, holding everything together. Conservative estimates put the halo radius at 250,000 light-years. That is the OW radius where material is gravitationally bound to the galaxy. But some models suggest the halo extends much farther. 400,000 light-years, 600,000 Jiao. Some calculations push it past 1 million light-years, a million light-years. If true, that makes the Milky Way 20 times wider than the old textbook. Measurements 20 times more space under our gravitational control picture. The scale Andromeda sits 2.5 million light-years away. If our dark matter halo reaches 1 million light-years out, and Andromeda's halo does the same, only 500,000 light-years of truly empty space separates us. The halos might already be touching two invisible clouds of dark matter, interpenetrating, mixing, preparing for the eventual collision. We cannot see the halo directly. Dark matter does not emit light, does not absorb. Light does not interact with electromagnetic radiation at all. It only interacts through gravity, but that gravity is real, measurable. Powerful researchers map the halo using indirect methods. Satellite galaxy orbits reveal where mass concentrates. Gravitational lensing shows where space curves. Computer simulations predict how dark matter should distribute based on galaxy 4. You are inside the halo right now. Dark matter surrounds you, passes through you. Earth is swimming through a sea of dark matter particles moving at hundreds of miles per second. Trillions of them stream through your body every second. You feel nothing. They pass through normal matter like ghosts. Scientists are trying to detect dark matter directly. Deep underground laboratories wait for a dark matter particle to bounce off a normal atom. So far, nothing. The particles are too shy, too rare, or we are looking in the wrong way. If the halo truly extends 1 million light-years, the Milky Way claims an enormous volume of space. Most of the local group falls within our sphere of influence. We are not just a galaxy, we are a galactic empire, a superstructure of invisible mass, dominating everything around us. And if our halo is this large, every other galaxy has one too. The universe is not mostly empty space, dotted with galaxies. The universe is mostly dark matter halos, with galaxies embedded in their centers like seeds and fruit. Everything we see is a tiny fraction of what exists. The visible universe is decoration on an invisible scaffold, 1 million light-years of darkness. That is the Milky Way that is home, and we are just beginning to understand how enormous it truly is. The galaxy is spinning too fast. It should fly apart. Stars at the outer edge orbit at speeds that make no sense. They should escape into intergalactic space. They should obey Kepler's laws of motion. They should slow down. As you move away from the center, they do not, and nobody fully knows why. Here is the problem. In our solar system, planets farther from the sun orbit slower. Mercury races around. In 88 days, Earth takes 365 days. Neptune takes 165 years. The farther out you go, the weaker the sun's gravity, the slower the orbit. This is basic physics. Isaac Newton figured it out 300 years ago. Galaxies should work the same way. Most of the mass sits near the center. Stars farther out should feel weaker. Gravity, their orbits should slow down. When you measure their speeds, you should see a nice curve decreasing with distance. Except that is not what happens. Stars at the edge of the galaxy orbit at nearly the same speed as stars closer in the rotation curve stays flat. This is impossible unless there is more mass out there than we can see. Dark matter, always dark matter. The invisible halo provides the extra mass. It extends far beyond the visible stars, keeping outer objects moving fast. The flat rotation curve is the smoking gun, the proof that dark matter exists in huge quantities. But here is where it gets strange. Even accounting for dark matter, the speeds are higher than predicted. Some stars in the outer halo move at 130 miles per second. Others hit 150. These velocities are barely below escape velocity. The stars are almost fast enough to leave the galaxy entirely. Why do they orbit so close to the edge of escape? What fine-tuned mechanism keeps them bound, but barely? This is called the escape velocity problem, and it haunts astronomers. One possibility is that we still underestimate the galaxy's mass. Maybe there is even more dark matter than current models suggest. Maybe the halo is denser at the edges than we think. Maybe our mass calculations are still wrong. Another possibility is that the galaxy recently grew. If the Milky Way devoured a large dwarf galaxy in the past few billion years, the merger could have injected stars into fast orbits. These stars have not had time to settle into stable paths. They still carry the energy from the collision. Evidence supports this idea. The Sagittarius dwarf is being torn apart. Right now, its stars are scattering into the Milky Way's halo at high speeds. In a billion years, those stars will look like native halo stars, fast, barely bound, mysterious. But what comes next is even stranger. Some stars move too slow. Hypervelocity stars in reverse. Objects that should orbit faster based on their location, but do not. They drift along like they are trapped in molasses. Nobody has a good explanation for these either. The rotation curve should be simple. Measure speeds, calculate mass, everything fits instead. Every new measurement reveals more anomalies, more outliers, more stars doing things they should not be able to do. This is where dark matter theories get tested. Different models predict different rotation curves. Warm dark matter produces smoother profiles. Cold, dark matter creates lumpier structures, self-interacting. Dark matter behaves differently in galactic cause so far. Cold, dark matter fits best, but the fit is not perfect. Discrepancies remain small. One's nagging. One's the kind that might point toward new physics, or might just be measurement error. The galaxy spins faster than it should. Stars orbit at speeds that defy simple explanations, and the larger galactic size makes the problem worse. More volume, more stars, more weird velocities to explain. Physics works everywhere else in the universe. It works in solar systems, in star clusters, in galaxies, far away, but in our own backyard. In the Milky Way's rotation curve, something is still not quite adding up. The Milky Way has 4 major spiral alarms, or maybe 5, or maybe 6. Astronomers are still arguing for decades. The textbook answer was 4 arms: Scum, Eurus, Normanus Perseus, Sagittarius. Each arm a river of stars, gas and dust spiraling outward from the galactic center. These arms trace regions where new stars are born. Bright, dense, easy to spot. Then better telescopes arrived. Infrared instruments that see through dust. Radio telescopes that map hydrogen gas. Space-based observatories above atmospheric interference. Each new tool revealed features we missed before the far 3 kilopasec arm appeared. First, a minor spiral arm hiding behind the galactic core. We could not see it with optical telescopes because the center blocks the view, but infrared instruments cut through the dust there. It was an entire arm, thousands of light, years long, right under our noses. Then came hints of other structures. The local arm where our solar system sits might actually be a major arm, not just a minor spur. New observations suggest it connects to larger structures. Farther out, what we thought was a branch might be a whole limb. The outer arm posed another mystery. It sits at the extreme edge of the visible galaxy. Some researchers thought it was just scattered stars. No real structure, but detailed mapping revealed organized spiral patterns extending far into the outer regions. The galaxy has structure where we thought it was empty, but here is the truly bizarre part. Nobody knows how spiral arms form. We see them in almost every disk galaxy, beautiful, elegant spirals, but the physics behind them remains murky. Here is the problem. Stars orbit the galactic center at different speeds. Inner stars orbit faster. Outer stars orbit slower. If spiral arms were just concentrations of stars, They would wind tighter and tighter over time, like stirring cream into coffee. Within a few rotations, the arms should blur into a smooth disk. They do not. Spiral arms persist for billions of years. This suggests they are not material structures. They are density waves, regions where stars temporarily bunch up, creating the illusion of an arm, like cars bunching in a traffic jam. The cars move through the jam, but the jam stays in place. Density wave theory works mathematically, but observations keep finding exceptions. Some arms have too many young stars. Others show gaps where stars should be. The outer arm appears too massive to be just a wave. It might be real structure material pulled out during a galactic collision millions of years ago. The bigger Milky Way size complicates everything. More space means more room for structure. Arms can extend farther. New arms can form in regions we thought were empty. The spiral pattern becomes more complex. Recent surveys using the Gaia spacecraft mapped 1 billion stars with incredible precision. The data revealed substructure within the arms, branches, spurs, gaps. The spiral pattern is not clean. It is messy, chaotic, like tree branches growing in every direction. Some researchers now argue the Milky Way is not a grand design spiral at all. It might be a flocculent spiral, a galaxy with patchy, poorly defined arms. This would explain why different surveys find different arm counts. Everyone sees different features depending on what they measure. The debate continues: more telescopes, more data, more arguments at conferences. But one thing is certain: the Milky Way is more complex than the simple four-arm diagram in textbooks. Hidden structures fill the galaxy arms we missed for decades, and if we missed entire spiral arms in our own galaxy, what else have we overlooked? What other features hide in the darkness, waiting for the right instrument to reveal them? Draw a line marking the edge of the galaxy sounds simple. It is impossible. Galaxies do not have boundaries like countries or continents. No border wall, no sign saying now. Leaving the Milky Way, stars just thin out gradually, slowly until there are none, or maybe a few scattered stragglers. Where exactly does that become not the galaxy? This is not a philosophical question. It is a practical problem. Astronomers need a definition, a standard measurement, a way to compare galaxies, but nature does not cooperate. The universe does not care about our need for clean categories. Several definitions exist, none of them perfect. The optical radius marks where visible stars become too faint to see. This gives you the bright disk, the obvious part, 100 light years for the Milky Way. But this ignores all the faint stars, dim dwarfs, and scattered halo objects. It is like measuring a city by counting skyscrapers and ignoring all the houses. The OWL radius is more scientific. It marks where objects are gravitationally bound to the galaxy. Inside this radius, stars orbit the center outside. They drift freely for the Milky Way. This gives about 250,000 light-years, much better. But even this has problems. Some stars outside the Vial radius still move with the galaxy. They share our motion through space. They formed here. Are they part of the galaxy or not? The OWL radius says no. Common sense says maybe then there is the dark matter halo. It extends far beyond everything else. If the halo reaches 1 million light-years out, is that the real edge? Most astronomers say no. The Holophadis. So gradually that choosing any boundary is arbitrary. It is like trying to mark where Earth's atmosphere ends. Technically, it extends thousands of miles up. Practically, it is gone after 100 miles. Where do you draw the line? The situation gets worse when you consider galactic winds. The Milky Way produces massive outflows of gas. Supernova explodes, stars shed material. This gas blows outward into intergalactic space, hundreds of thousands of light-years out. Is that material still part of the galaxy? Some of it will fall back. Gravity pulls it down. The galaxy recycles its gas over billions of years, but some escapes forever lost to the void. At what point does gas stop being Milky Way gas and become intergalactic medium? The Malin stream adds another complication. The large and small Malan clouds are leaking gas as they orbit us. This gas forms a stream, stretching across the sky. Is that stream part of the Malan clouds, part of the Milky Way, or neither? All three answers have defenders. Andromeda poses the same problem from the other direction. Its dark matter halo might already be touching ours. When two halos overlap, where does one galaxy end and the other begin? The space between becomes shared territory, co-owned, disputed. This is not just semantics. The definition affects mass estimates. It affects size comparisons. It affects our understanding of when the Andromeda collision truly begins. If the halos are already merging, the collision started millions of years ago. We are living inside it. Most astronomers settle on practical definitions. The disk ends where star formation stops. The halo ends at the vial radius. The dark matter extends as far as simulations suggest. Each definition serves different purposes. None of them perfectly captures reality. Here is the truth. The Milky Way is not an object. It is a region, a zone of influence, a gravitational neighborhood. It has a dense core, a structured middle, a diffuse edge, and beyond that edge, it fades into something else. 200,000 light-years is our current best answer. But ask that question again. In 10 years, new measurements will change it. They always do. The galaxy has no edge because the universe does not work that way. Everything blends. Everything connects. We live in a cosmos without borders, and we are still learning to measure it. There are stars at the very edge of the galaxy moving at insane speeds, 130 miles per second. 150, some hit 200. They should escape. They should fly off into intergalactic space. They do not. Something holds them. These are called high-velocity halo stars, not hypervelocity stars, which move fast enough to escape. Halo stars move just under that threshold, barely bound skating on the edge of freedom. Finding them was difficult. They're faint, distant, scattered across a huge volume. But surveys like Gaia tracked millions of stars with incredible precision. Measure position, measure motion, calculate velocity. Some stars lit up red flags immediately. One star traveling through the outer halo moves at 198 miles per second. The galaxy's escape velocity at that location is roughly 200 miles per second. This star is 2 miles per second away from leaving forever. It is like a rocket barely held by Earth's gravity. One small push and it is gone. Why do so many stars orbit so close to escape velocity? This is not random chance. Something put them there. Something gave them that specific amount of energy. But what galactic collisions offer one answer? When the Milky Way ate smaller galaxies, the collisions injected energy into the system. Stars from the dwarf galaxy received huge velocity kicks. Some escaped, others settled into fast, barely bound orbits. These survivors now populate the halo. The Sagittarius dwarf provides evidence. Its stars are scattering at high speeds as the Milky Way tears it apart in 1 billion years. Those stars will be indistinguishable from other halo stars. Fast, ancient, mysterious. But we caught this one in the act. We see it happening. Another possibility involves three-body interactions. When two stars pass near a third object, gravitational interactions can fling one star outward at high speed. This happens in dense star clusters. Occasionally, a star gets ejected with enough energy to reach the galactic halo. Most escape. A few land in that sweet spot fast, but not too fast. Black holes complicate everything. If a star passes close to a massive black hole, the gravitational slingshot can accelerate it to enormous speeds. The supermassive black hole at the galaxy center weighs 4 million suns. Any star venturing too close either gets eaten or flung away violently. We found several hypervelocity stars leaving the galaxy at speeds over 400 miles per second. These stars are escaping, no question. Calculations trace their paths back to the galactic center. Something near the black hole kicked them out. Maybe they were in binary pairs, and the black hole captured one star while ejecting the other. But the barely bound stars pose a different puzzle. They are not coming from the center. They orbit far out in the halo. Their speeds are high, but not extreme. They seem comfortable at the edge of the galaxy's gravitational. Well, one theory suggests the dark matter halo is lumpier than we think. Concentrations of dark matter at specific distances could create stable orbits at high velocities. Stars settle into these orbits naturally. This would explain why so many halo stars move at similar speeds. They are trapped in resonance with the dark matter distribution testing. This theory is hard. We cannot see dark matter directly. We can only infer its distribution from how stars move. But if the halo is lumpy, we should see groupings, clusters of high-velocity stars orbiting together. Some surveys hinted this, others find random distributions. The data is messy. Here is what we know for certain. The galaxy's outer regions are wilder than expected. Stars move faster than simple models. Predict the boundary between bound and unbound is thin, barely a few miles per second. Separates staying and leaving. If the galaxy is larger than we thought, more stars live in this dangerous zone. More objects skating at the edge, more potential escapees, and understanding why they stay reveals something deep about galactic structure, about dark matter, about how gravity works at enormous scales. Fast stars at the edge of the galaxy held by invisible mass, moving at impossible speeds, and we are only beginning to understand what keeps them here. The Milky Way is not special. If we measured our galaxy wrong, we measured all galaxies wrong. This is the terrifying implication, the realization that makes astronomers stay up at night, recalculating everything they thought they knew. Every galaxy in the universe might be twice as large as recorded. The cosmic census needs rewriting. Here is why this matters. Astronomers use galaxies to understand the universe, how matter distributes, how structure forms, how dark energy affects cosmic expansion. If the galaxies are all bigger than we thought, every calculation changes. Galaxy masses determine how they interact. Bigger galaxies have stronger gravity. They strip stars from smaller neighbors more easily. They dominate their local groups more completely. They form clusters differently, recalculate masses, and you recalculate galaxy evolution. The problem extends to distance measurements. Astronomers use certain types of galaxies as standard candles, objects with known brightness. Measure how bright they appear, calculate how far away they must be. But if those galaxies are bigger, their brightness changes. The distances change. The expansion rate of the universe changes. Dark energy measurements depend on precise distance calculations. Any error propagates through every cosmological model. If galaxies are universally larger, dark energy calculations shift. The universe might be expanding faster or slower than we think. Researchers are now revisiting galaxy surveys, the Sloan Digital Sky Survey, the 2-micron All-Sky Survey. Every major catalog, they are applying new measurement techniques, accounting for dark matter halos, using stellar streams and satellite galaxies, where available preliminary results are disturbing. Many galaxies appear larger, some by 50%, others by a factor of 2. The trend is consistent. We systematically underestimated galactic size. Andromeda is bigger, Triangular is bigger. Every major galaxy in the local group needs REM measurement. And if local galaxies are bigger, distant galaxies probably are too. The whole cosmic web might be denser than we realized. This has implications for dark matter. If galaxies are bigger, they contain more dark matter. The ratio of dark matter to normal matter shifts. This affects theories of galaxy formation. It affects predictions about how the universe evolved. It affects whether our cosmological models even work. Some researchers suggest the discrepancy explains long-standing problems. The missing satellite problem. For example, simulations predict large galaxies should have hundreds of satellite galaxies orbiting them. We only observe dozens. If our galaxy is bigger, its gravity pulls farther. Maybe those missing satellites exist, but orbit so far out, we have not found them yet. Another puzzle involves galaxy rotation curves. Many galaxies show the same flat rotation pattern as the Milky Way stars at the edge orbit too fast. This is why dark matter was hypothesized in the first place. But if the galaxies are bigger, The dark matter halos extend farther, the rotation curves make more sense. The physics fits better, but recounting creates new problems. If galaxies are bigger, the space between them is smaller. The universe becomes more crowded. Galaxy interactions happen more often. Collisions occur sooner. The timeline of cosmic evolution speeds up. This affects our understanding of galaxy clusters, large groups of galaxies bound by gravity. If each galaxy is bigger, their gravitational interactions become more complex. The cluster dynamics change, mass estimates shift, dark matter distributions need recalculating. Even the very early universe gets affected. Astronomers use distant galaxies to study cosmic history, galaxies forming billions of years ago. If those primordial galaxies were larger than measured, they formed faster than we thought. Structure assembled more quickly. The universe was more mature at earlier times than our models suggest. The implications cascade through every field of astronomy: stellar population studies, galaxy morphology, active galactic nuclei, supermassive, black hole evolution. Everything connects to galaxy size. We are recounting the universe, every galaxy, every cluster, every structure starting from scratch with better measurements, and the universe that emerges is bigger, denser, and more complex than we imagined. The Milky Way was just the beginning, the first domino, and the rest are falling. The Milky Way spins around a point, not the supermassive black hole, not the visible core, the center of mass. And we just realized that point is not where we thought it was. Center of mass is simple, in principle. It is the balance point, the spot where all the mass averages out. For a ruler, it is the middle for Earth and Moon. It is a point inside Earth, but offset from the center, because the Moon pulls for the galaxy. It is the location around which everything orbits. Astronomers assumed the center of mass sat at the galactic core. Makes sense. Most of the visible stars cluster there. The supermassive black hole sits there. Everything seems to point toward the center.